everyone. We've got quite a lot we want to try to get through in this presentation, so I thought we'd start with a bit of a take-home message summary at the front. Essentially, as we've heard from Sally Holbrook previously, there's been a global coral mass bleaching event running for the last several years, particularly unprecedented on the northern and central parts of the Great Barrier Reef in Australia in 2016 and 2017. That has led to the establishment of a collaborative research platform in the water at Moore Reef on the central Great Barrier Reef that aims to investigate fine-scale hydrodynamics and coral stress with a view to developing interventions that might help the corals survive future bleaching events. And what we've found so far is that it's not just a matter of global heating. Failure of normal wind-driven water column mixing contributes to coral stress over a period of a couple of days and contributes to resultant coral bleaching and mortality. Restoring this failed mixing at small spatial and temporal scales could restore near normal survivable temperatures for corals, and this would not take a lot of energy. And the results of our Reef Havens research project could be applicable to other reefs worldwide that sustain millions of people in the tropics. So the idea of focusing conservation effort on small refuges is well accepted terrestrially. Nobody fights about that, but it's a new concept for the Great Barrier Reef. While corals have considerable natural acclimatisation and adaptation capacity, the current rate of climate change and predicted future bleaching events is likely to outstrip that. So we need to identify potential reef refuges on the Great Barrier Reef that can then be actively defended using a range of science-based tools, and starfish control was mentioned earlier. Unfortunately, we currently have very limited knowledge about what any of these tools might be that we could use on the Great Barrier Reef, so we have to have a very strong economic argument for this project. So this is what it is. The Great Barrier Reef has a $6 billion per year tourism industry, which is obviously dependent on its health, and 60,000 jobs. 80% of that tourism industry relies on just 7% of the Great Barrier Reef. Great Barrier Reef is absolutely enormous. It's about 3/4 the size of this island of Madagascar. It's also compared in area to the size of Japan. So the fact that we can pinpoint just incredibly small parts of that area that are incredibly economically valuable. The majority of this tourism is actually pontoon-based off Cairns. So the pontoons don't move around, they're fixed in position. Which means that the relatively tiny snorkelling footprint around each tourism pontoon has extraordinary economic value. This is an aerial shot of our study site at Moore Reef, which is about 20 nautical miles off Cairns, and that box is about 1 kilometre each square and on each side. And you can see 2 tourism pontoons in position there. So during the 2016 and 2017 bleaching events on the Great Barrier Reef, which were unprecedented in their severity, it was clear that the response of the corals wasn't uniform. There was patchiness, fine-scale patchiness in bleaching severity and subsequent mortality. We observed that corals that have access to cooler and or flowing water do better during bleaching and then recover better afterwards. And this can happen on a scale of less than 10 metres. So you can have coral colonies side by side, apparently the same species, react very differently to the bleaching event. So we realised that we don't know enough about the fine-scale hydrodynamics that occur during bleaching events, and that's one of the reasons why we've set up the Reef Havens research platform, which is a collaborative in-water research and monitoring platform that will enable testing of science-based local-scale interventions for biodiversity conservation on the Great Barrier Reef. And we aim to provide actionable advice about the utility of engineering approaches to reducing heat stress at local scales. We have independent science oversight, We have an array of benthic flow and temperature meters and loggers installed at the site at Moore Reef. We have a range of other instruments that allow us to look in detail at temperature in the water column, and we have the ability to measure coral stress on a daily basis, and we have over 200 million data points collected to date. All of these data are being made publicly available, and I'd just like to acknowledge that this research project is only possible thanks to the Australian government funding and ongoing close collaboration with the marine tourism industry, the Great Barrier Reef Marine Park Authority and the Australian Institute of Marine Science. So I'm just going to hand over to my colleague Dennis Stanley from the University of Western Australia, who's going to talk a bit more about the fine-scale hydrodynamics during the bleaching event on the Great Barrier Reef.
Thank you, Suzanne. A lot of this talks, I'm going to be talking about calm wind conditions. There's a term used by NOAA called the doldrum day. I'd just like to explain that. That's a day when there's less than 3 metres per second wind. Okay. During 2017, these doldrum days, less than 3 metres per second wind, were a very big feature of this event, with more than twice the number occurring than would normally occur in this part of the season. Slide. Okay. What we've got here is a time series of the reef logger temperature. Okay, so this is a long-term monitoring system that's been in place in Moore Reef, and this is the temperature that the corals experienced during the event. The orange line is a climatology made up from 20 years period of data from that logger. Okay? So this orange line essentially represents what a normal season should look like, and the red curve is what actually happened during 2017. I'd like you to notice that the top of climatology here is 29.3. That's what the corals in the region are climatologically adjusted to survive in. We have these three peaks. Well, this is sort of split peak. late January, late February, and nearly all of March. Okay? These three high temperature events were associated with bleaching, and this one in March was particularly severe. Next piece. Now, when you overlay the occurrence of those doldrum days on the temperature graph, it becomes apparent that the solid red dots are where the doldrum days occurred, and the hollow dots are when it was almost a doldrum day. That's less than 3.5 metres a second. Okay. So we see that periods of calm weather are associated with the temperature stress events. But also, we have these periods coming back to normal, almost normal climatology. Okay? And that inspired us to go look what they were and see if there's something we can do. Now we've plotted wind onto this graph. Now underneath there's the daily wind average, the daily average wind, and this heavy trace is the average wind for the last 7 days. Right. And what we see is every time we have a decent period of normal wind conditions, then we have a lull in the temperature. In the reef temperature. Okay, so every string of doldrum days is a climb away from climatology. Every string of windy periods is a string back to climatology. Now, what we're seeing here is just some pretty well understood oceanographic processes playing out. Okay, the sun is heating the surface water in the ocean. That water is heating and expanding, and it floats on top. It needs these wind-driven mixing processes to distribute that heat through the water column. If those mixing processes fail due to strings of doldrum days, then it leaves the surface water trapped, that hot, less buoyant water trapped in the surface where it can be repeatedly heated day after day. Additionally, there's nighttime cooling that happens that helps alleviate that, and that happens mostly by evaporation. The evaporation is also proportional to the wind speed, so in these doldrum days, that heat loss is also dropped. So you get hot water trapped in the surface because it's not being mixed down through the water column. Ocean gliders are autonomous sampling instrument. IMOS and the Australian Institute of Marine Science deployed one of these in response to this event, and we managed to capture about 7 days of data during this event. Next slide. Okay, so this is an ocean profile. We have temperature depth down this axis, starting at the surface, coming down to 40 metres. And we have the water temperatures displayed along the bottom. I split the profiles up into blue profiles. These are ones taken during the night, okay? And red profiles taken during the day. This particular slide is after a period of 3 windy days, or 3 normal wind days, right in the middle of the bleaching event. There's a few important things to note about this slide. One is that the water column at night time is completely mixed all the way down because it's all the same temperature. So what's happening there is that heat that's being delivered in the day is being transferred and distributed over a large volume of ocean water. The average temperature of the water column is 29.3 degrees. That's spot on the climatological maximum for the year and completely survivable for these corals. Up here in the top are the logger data from the reef loggers displayed on the same graph for the same time period. And you see these big temperature variations day to night. That's normal for this time of month. This is a part of the tidal cycle where these loggers are in shallow water when these measurements are taken. So the same amount of energy is acting in shallow water, so the temperature difference is big. But it really demonstrates that daytime heating, nighttime cooling, and of course what the corals are adapted to surviving at a very short time scale. Okay. Now this is what happens after 3 or 4 doldrum days. We've got all this very hot water, very buoyant water, floating in the top of the water column, being successively heated day after day. Okay? That is not being mixed through the water column, as we did in the first slide, because the processes of wind-driven mixing have failed. The water column temperature, however, is only 29.5 degrees on average. So the actual water column itself has hardly got hot at all. It's only got hot by 0.2 degrees. It's completely survivable for the coral. But the surface water, where all this buoyant hot water is now trapped because the mixing processes have failed, is what's putting the coral under stress. Okay, next slide. This is essentially the same data, just presented in 3 days of the windy conditions and the 3 days of the calm conditions. What this demonstrates is that that surface mixing upset or failure really affects only the top 10 to 15 metres of the water column. Below that, it's unaffected. The green line is that climatological maximum, and we can see at a depth of 25 metres during the 2017 bleaching event, perfectly normal temperature was available for the coral. So the coral was bleaching on the surface, and 25 metres away, there was normal temperature water. If we tie the observations of our co-author Eric Fisher, these are observations of the onset of bleaching. The observation of onset of bleaching in the February part, in the January part, was associated with a string of doldrum days. In February, it was also associated with the doldrum days, and this long period of March, greater than 2,000 colonies at this site bleached. Well, it raises the tantalising question. Could a system that supplementally mixed that water and restored that water column mixing that's missing during those 3 days, restore the homogeneous water column back to that 29.5 degrees, which is survivable for coral? That essentially gets down to how much energy would that take. Yeah? So this is a slide that assesses how much energy that takes. I'm not going to bore you with maths, don't worry. I've set up a hypothetical situation of 10 metre column of water, stratified top 5 metres, bottom 5 metres, 1 degree temperature difference. And then evaluated the gravitational potential energy difference between the stratified state and the mixed state. It comes out at 40 joules per square metre, 42 joules per square metre. If we extend that to a 1 kilometre square, 10 metres deep, that's 40 megajoules. If a hypothetical system of 20% efficiency were deployed, that would take 60 kilowatt hours to fully mix that water column, or to overcome that stratification. So what does 60 kilowatts look like for what we're already doing on reef tourism sites? Well, it's 2 minutes operation of a passenger ferry, it's 20 minutes operation of a joyfly helicopter, it's 2 hours operation of a 40 horsepower outboard, or it's 8.5 or 7.5 hours operation of a 10 kVA genset. So the energy requirement to do this mixing is trivial compared to what things are already happening on the reef tourism site. So that's basically the summary. In least some coral bleaching events, the fire of mixing contributes to coral thermal stress. Restoring the normal mixing is energetically feasible at the scale of a reef tourism site. The technology achieved, the mixing is available. So, let's do it.